Hello class, this is Mr. Koi. The iPad is up and working, so we are on to more videos. So we're still working on conservation of energy. So for practice, try the problems first, then watch the video to check if you have done them right. If you just watch the video and copy, you will not get as much out of it. Alright, so this is still a dog in a roller coaster, but I feel like we didn't have as much time as I wanted to go over D and E. So I am going to go over them in this video. So again, look at the roller coaster, try D and E, come back to me. Now that you're back, first always read the problem. D. At how many other places on the track will the dog be traveling at exactly the same speed as at point C? Mark each of these points on the track with a star. So just a quick note, in case you're not sure, that is C, that red dot. So this is a more conceptual question. You don't really have to calculate if you understand what you're doing. So we know that since this is a closed system, that means energy is conserved. Nothing is lost or gained. So in this entire system, energy stays the same. It changes forms, but the total amount of energy is exactly the same. So the amount of energy here, the sum of all energy here, at A, is exactly equal to the sum of all energy at C. Let me make that C smaller, at point C. So, but we know that for the speed to be exactly the same, the kinetic energy at each place has to be exactly the same, because the dog hasn't changed weight, so if it's not going to change speed, the kinetic energy would also have to be the same. So is there any place where the kinetic energy is exactly greater, or is exactly equal? And that, we also know that it has to be, the kinetic energy has to be equal, and since everything adds up, the potential energy has to be equal at C to whatever other place. So we think, is there any other place where the potential and the kinetic energy equal? Well, we know the potential energy has to do with height. Since there are no other places at this height, it is the only one. There is no other places. Only C has that exact place. For example, though, if we picked a different place, say if I wanted to pick right here and call it D. So if we were looking at D, we can see, oh look, there's a couple different places where it's the exact same height. It would also be going the exact same speed. If this is still confusing, try watching a couple times, Googling it, and then come seeing me for extra help if you still need it. Moving on to E. So at the end of the track, the dog will crash into a spring. If the spring constant in that spring is 14 kilograms per second squared, what distance will the spring be compressed when the dog comes to a stop? So there's a lot of things going on in this problem. It is a conservation of energy because this is a closed system. So remember, we know that the amount of energy at the beginning, such as A, is equal to the amount of energy at the end next to our spring. If we know that, we know a lot of different things. So we know that at the beginning, at A, we have kinetic energy and gravitational potential energy at A. At the end, what kind of energy do we have? So the dog will be stopped, so there's no kinetic. The dog is on the ground, so there's no gravitational potential, excuse me. The only one there is spring potential energy. So after this, we can start in adding our equations. So we know it's 1/2 mv squared plus mgh at point A, and the spring potential is 1/2 k squared. Okay. Now we want to look to plug in some numbers. We know that our mass of the dog, so now we can put in numbers. 1/2. The mass of our dog is, if you look in the problem, It's 20 kilograms. Its initial speed is 2 meters per second squared. Add this to, again, we have our mass times gravity. I'm going to abbreviate to 10 because I'm doing a lot of this math in my head. Meters per second squared. Then the height at this point is 14 meters. This is all equal to 1/2. Alright, and it says, remember, K is the spring constant. So this is where, so K is 1400 kilograms per second squared. And then we are looking for x, which is our distance. We don't know yet. Alright, after this, it's an algebra problem. So I'm going to erase some things down here so I have more room to write, and I'm just going to write over this. Alright, so now it's do the math. We know that 2 squared, hopefully you know that 2 squared is 4 meters seconds squared. Remember, it transfers to both of them. We have 20 kilograms, except half of 20 is 10. So it's 10 kilograms. Plus, we now have 10 times 20. So that's 200 kilograms meters per second squared times 14 meters. I'll need a calculator for that one. And then we have a half of 1400 be 700 kilograms per second squared. And we still don't know what x is. Alright, so I'm going to essentially, so this is going to be 40 kilograms meters per second squared plus 2,800 kilograms, and we have meters times meters here, so it's meters squared over second squared. Notice these have the same units. That's good. That means we can add them easily. So you have 2,840 kilograms meters squared over second squared is equal to 700 kilograms second squared. And we're going to times x squared. So to get rid of this, remember we want to divide on both sides by this. Cross them out. This would be 700 kilograms per second squared. These are both on the bottom. They cross out here. We're left with meters squared, which is probably good because we were talking about distance. Then we divide these. When we divide, we get 4.1 meters squared is equal to x squared. To get just the distance, square root both sides. So the total distance is x equals would be 2.0. So roughly 2. Really small number. So almost exactly 2. Alright, hopefully that helped you on how to deal with springs. It's not any more difficult. It just might sound a little more complicated, but really in the end it all just boils down to the algebra. Remember, if you can get to this stage and you mess up your calculation, I will still give you most of the points. Alright, try these really quick, and then I'm going to quickly go through them. Hopefully they seem familiar. If they don't, fine. If they do, still go over them again. I doubt, unless you haven't completely memorized the answer. Alright, so it's asking about the kinetic energy right before it hits the ground. Therefore, we know that in the beginning, it's on a ledge and it's going to fall. At the end, it's about the ground to hit the ground. So here we have gravitational potential energy. And here we have pretty much all kinetic. There might be a little teeny bit of gravitational potential, but for our purposes, it's pretty much all kinetic. So we know that in this case, the kinetic energy at the end is going to be equal to the potential energy at the beginning, because those are the only types of energy present at each point. So we know this is mgh is equal to 1/2 mv squared. We do want to find the velocity, but we know everything else because it is a 8-kilogram flower pot. Gravity is in effect, so it's 10 meters per second squared. The height is at 12 meters. This is equal to 1/2 8 kilograms times v squared. Notice we have 8 kilograms on both sides, this m here. We can just go ahead and get rid of it, so you don't have to bother. Easier, makes the math easier. So 10 times 12 is 120 meters squared, seconds squared. This is equal to 1/2 v squared. So you divide by 1/2 on both sides, which is the same as multiplying by 2. You get 240 meters squared over seconds squared is equal to v squared, and square root that for both sides for your answer, which will give you velocity equals 15.5 meters per second. So I noticed I did skip right to the end, but it would be the same thing. mgh would just be exactly equal to your kinetic energy, since they are the same. So it would just, instead of, it'd be that 12 meters times 10 gravity times 8, which should be 1920 joules. Remember, unit for energy is joules. Alright, so then a ball is fired up into the air, so your before and after picture. Your ball would start down here. It's really not far off the ground, so it only has kinetic energy. And up at how high it will go, at the very top. It's really not going to be moving, but it's at the top height, so it's going to be its potential energy, gravitational to be exact. We know that it has 200 joules of energy here. That means it has to have 200 joules of energy here. So we know 200 joules is equal to the gravitational potential energy, which is mgh. And then we know that the mass is 2, gravity is roughly 10, and height we do not know yet.
Just so that I have like the 3 versions, but I know that's a lofty goal.
So the height is 10 meters. On the next one, similar idea. However, now our ball is only halfway up.
No, it's okay. Me and the 2 physics.
So it's still going up, but it's also still moving, so it has kinetic and potential. So I know it's halfway up, so that means it's at 5 meters, because we just found this to be 10. So we know that 200 joules is equal to our potential and kinetic, so the mgh plus 1/2 mv squared. It's 2 kilograms, still 10, this is 5, 2 times 10 is 20, times 5 is 100, so we subtract 100 from both sides. So I have 200 minus 100 equals 100, equals 1/2 2v squared. This cancels out to 1, square root both sides, equals 10. Alright, next is, let me actually clear everything. Next we have a kid, he's on a hill.
So there's no telling that, like,
at the end, she's at the bottom. So at the beginning she was pushed, so she has kinetic energy, and she's at the top of the hill, so she has potential energy. At the bottom, she's at the very bottom, so she only has kinetic energy. So I want to know how fast she's going. So I get to go 1/2 mv squared is equal to, or plus, excuse me, mgh is equal to my later kinetic energy of mv squared. This is initial height and initial velocity. So we notice we have mass in all of them. We can cross all of them out. So we have 1/2 v squared, this is 6, plus gravity, 10, times our height, which is also 10 meters, and 1/2 times the v squared we don't know. This is 36, times 1/2 is 18, 10 times 10 is 100.
And he said, I imagine we will move the second week, although you're not.
Multiply by 2 on both sides. Alright, from here, square root. Alright, and then you solve it, and it's 15.4. Alright, then we can do the same sort of idea. Hey, look, this is my total energy. I just added it. Oh, excuse me. Sorry. This is my total energy. 118. So I know if I'm going to go up another hill, so now instead of just kinetic, if I'm at the top of a hill, it's going to be just potential. So that 118 is now equal to only potential energy. My mass hasn't changed, gravity hasn't changed, but my height has. So the height is equal to, and in my rush I of course forgot that we crossed out mass this entire time. So that's 10. Sorry about that, guys. That's what I get for going faster, remembering old problems. Alright, last but not least. Alright, last one, above the spring constant. So that's K is equal to 300 Newton meters. And it stretches back 30 centimeters. Remember, we want this in meters, so that's the distance, x, is 0.3 meters, which is equal to 30 centimeters. But that's the one we want. Alright, then I want to know how fast it will be going. And the mass is 300 kilograms, which would be 0.3, or 300 grams, 0.3 kilograms. Alright, so again, do your before and after. So before, our bow is stretched back, so there is spring potential energy here. Later, when our arrow is going, this is only kinetic energy. We've released all of our spring energy. So we can say spring energy is equal to our kinetic energy. So now you put in your equations. And this is 1/2 kx squared. So it's 1/2. K is at 300 Newton meter times x squared. X is 0.3. We have to square it. 1/2. Excuse me. Mass is 0.3. And then we don't know what v is yet. This is 0.15 v squared. Multiply those together. Alright, so I did skip some math here. Hopefully this is what you got. And that would be 90 squared, square root both. And this makes v equal to 9.5.